11:01. So, if you recall, as we've been discussing, we've been using Laplace transforms to solve linear or linearized models of processes. And even though we're interested generally in the output as a function of time, so if it's a reactor, it could be the concentration as a function of time, it could be the temperature as a function of time, we found it's convenient or much easier to actually do the algebra if we take the Laplace transform. So by taking the Laplace transform, we turn the derivatives into, and integrals into algebraic quantities, which we then can solve algebraic equations, pretty easily, more easily than differential equations. But if we want the output as a function of time, we still have to do the inverse. And to do the inverse, that first we do partial fractions, which requires a little work, and then we have to hopefully find all of the terms in the partial fraction decomposition of the answer in our table. And that requires some work. The question is, do we really need to know the detailed functions, CA as a function of time, or temperature as a function of time? Maybe we only need to know certain characteristics of that solution, and not all the details. Of course, it depends on our goals, but most of the time, we don't need to know everything. So for example, what are things we might want to know? Well, we certainly want to know, is the system going to blow up? We really want to know that. Do we, that's a really important piece of information. Is it going to blow up? If it's not going to blow up, then is it going to go to a steady state? If it goes to a steady state, what is that steady state? Now that steady state is the infinite time solution. I don't necessarily need to know what happens in between. Sometimes I do, sometimes I don't. I might also want to know, how does it go to the steady state? Does it go there just exponentially, or does it oscillate and decay? I might also want to know what happens when I have different kinds of inputs, different kinds of disturbances. So our inputs, typically, so far this semester, the disturbances have been either a step function in some variable, in some input, a pulse, which we call a Dirac pulse. And what we're going to look at today is we're going to look at sinusoidal inputs. So inputs that oscillate in time. We're going to look at all those. And what kinds of things are we interested in? Info that we want. As I just said, well, we want to know, will it blow up? In other words, stability. If not, does it oscillate? Does it go to steady state? If so, what is that steady state? And as we spoke about at the very end of the last hour, if I have a sinusoidal input, what is the frequency response? So the frequency response what does that mean? That means, what is the frequency of the output? What is the amplitude of the output? And what is the phase lag? we'll talk about all those. Now, as we said, when we have a Laplace transform of the solution, when we have the solution in terms of s, not in terms of the function of t, then in order to do the inversion, to get it as a function of t, there's some work involved. You have to do the partial fractions, and then you have to look up each of the pieces that come out of the partial fractions in your table and try to do the inverse. Maybe you can get answers, maybe, if you're lucky, to these questions without ever doing the inverse. So that's the question. Can we answer 1 through 4 without inverting? And as we'll see today, the answer is yes. If all you want to know are these things, you don't have to invert. Like a miracle. If you want more information, you got to invert. But if this is what you want, and often this is all you need, you don't have to invert. So let's start with, will the system, let's do the simple ones that we've sort of done already. Can we answer 1 through 4 without inverting? Question mark, question mark. So let's look at the ones we've done already. Does it go to a steady state? And if not, if so, what is that steady state? Well, that one, so question 3, we can use the final value theorem. So let's answer question 3 right now. Let's say I have so question 3, I want the limit as t goes to infinity. Does this exist? Does limit exist? Of some answer, say y prime of t. No tilt. I want to know, does this thing exist? And if so, what is it? Well, from the final value theorem, I know that, well, even before that, this is the limit as t goes, well, from the final value theorem. This is the limit as s goes to 0 of y prime tilde of s. And that's equal to, in terms of these g's, remember we said g is our transfer function, that's y prime tilde over x prime tilde. So y prime tilde is just g tilde x prime tilde. So I just do that. I just take that. If that limit exists, then the system goes to a steady state, and I can find out what that steady state is. And I didn't have to invert. I leave it in terms of g tilde. Now let's look at a specific example, or something specific, where x prime of t is a step. So this is an example where it's a step. If x prime is a step, then this is the limit as s goes to 0 of g tilde of s. And by the way, I left out an s. It's s times that. S times s. S times y tilde of s, the final value theorem. So, s g tilde of s. And now x prime, if x prime is a step, then this is just delta x over s. The s's cancel, and this is just the limit as s goes to 0 of g tilde of s times delta x. So that is the answer, and in fact, let's just rewrite it for a step for x prime of t a step, i.e. x prime versus t, this is 0, it goes from 0 to some value, and this is delta x, and this is t is equal to 0. When x prime is a step, then y prime is delta y. It's y at infinity minus y of 0. Delta y over delta x at steady state means as t goes to infinity, we call that Kp, the steady state gain. That's the definition of steady state gain. And we see that this is just equal to the limit as s goes to 0 of g tilde of s. So directly from g tilde of s, we get the steady state gain for a step function in time. We just get, so Kp is just the limit as s goes to 0 g tilde of s. By the way, I didn't erase this because last time we looked at the initial value theorem, which was the limit as s goes to infinity. Here it's the limit as s goes to 0. Any questions on that? That's something we did last time. We already did earlier. Okay, so that's question 3. We've taken care of question 3. Will the system blow up? Stability. We spoke about that last time, last week, where we looked at the alphas. We had the answer in terms of s. It was a ratio of polynomials. We factored the denominator to get all the roots of the denominator. And by looking at the roots, at the real parts of the roots, we were able to answer the question, will it blow up and does it oscillate? If the roots are complex, it can oscillate. Will it blow up? That depends on whether the real parts are all negative or not. So we answered these already. And again, we answered it without having to do the inverse, just from looking at the list of the alphas, of the roots of the denominator. So what we have left is the frequency response. And the frequency response, I gave an example last time. I didn't really give an example, I just sort of said, if we have an input and an output, well, is the frequency of the output the same as the frequency of the input or different? Is the amplitude of the output, the amplitude, how high this is, which is I can call B, and this I can call A, the amplitude of the input. Is the amplitude B, how does that relate to the amplitude A? Amplitude is I have an oscillation. How big is the oscillation? And finally, are they in phase or out of phase? That is, when the input is at its maximum, is the output at its maximum or is the output somewhere else? Or is there a lag? The input is at its maximum, but the output hasn't reached its maximum yet. They could be out of phase. So how do we know those things? Those are important things to know. So let's think for a second of some extreme cases. Let's think 2 extreme cases. One of them, the input oscillates very, very slowly, extremely slowly. So the period is like infinite. So you could think of something, for example, where you have a reaction that takes place in a millisecond, in a few milliseconds. Well, and there's the temperature outside, which oscillates from day to night. So it has a period of 24 hours. Well, if I have a reaction that goes on in milliseconds, it doesn't really, it's so fast that it's always at the steady state consistent with the outside temperature. Because before this outside temperature changed even a tiny bit, it's already found its steady state. So if the time scale of the oscillation is much, 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 much slower than the time scale of everything in my system, the system's always in steady state. That's not an interesting case. It's always in steady state. So obviously, it's going to move with the input. On the other hand, what's the other extreme? The other extreme is where the oscillation is much faster than the time scales of the system. Remember, when I say the natural time scales of the system, I'm talking about that capital T that we had when we had first order linear differential equations. We had dy dt plus ay. A was 1 over time. So that 1 over a was the characteristic time scale of my system. So if the time scale of the oscillation is much faster than the time scale of the system. So I have a system, maybe the temperature in this room, it changes in tens of minutes. If I open the window, it's still going to take maybe 10 minutes for the temperature to noticeably change here. On the other hand, if I have a heater that's going on and off 100 times a second, because it's broken, it's going on, off, on, off, on, off, on, off, then the system, the room, is not going to see the on and off. It's just going to see the average. It's going to see the average amount of heat that comes out per minute. It's not going to see that it went off, went on, went off, went on 100 times a second. So those are the two extremes. Those are not the interesting cases. But you always want to kind of know the extremes before you start on the interesting case. The interesting case is something in between, where the time scale of the oscillation is in the ballpark of the time scale of your system. And again, when I say very fast or very slow, you have to notice, I always have to qualify, what do I mean by very fast and very slow? I mean relative to the time scale of the system. Something can be very fast compared in one system and very slow in another system. It all depends on the time scale of that system. So for example, the oscillation of the temperature from day to night is very slow compared with the reaction that goes on in milliseconds. But it's very fast compared with the degradation of the building materials of this building, which is more like decades. So day and night temperature, super fast. Okay, so let's look at a situation, let's look at an example where I can illustrate what these guys are. So let's say I have a CSPR. So this is an example. No reaction. But I have the input concentration goes from one value to another. And let's see what I have here. So if I write out dCA in dt. Actually, do I want to do it that way? No, actually I want to change that. That's not what I want to do. I want, it was steady state for a while. This was steady state, and at t is equal to 0, I oscillate. I have a sine input. So in this case, the sine input is A sine omega t. So that's the situation I want to look at. Okay, so dCA dt is equal to the input, Ca in minus Ca over tau, where remember tau is the volume of the volumetric flow rate. And for t less than 0, the system's in steady state. And now what I want to do is, I notice that Ca in is going to change. Well, let's separate things out here. I have dCA dt plus Ca over tau is Ca in over tau. Okay, and at steady state, let's go through the steps. At steady state, dCA for t less than 0 dt plus Ca for t less than 0 over tau is Ca in t less than 0 over tau. And I subtract, and I have dCA prime dt plus Ca prime over tau is equal to CA in prime over tau. So I'm being a bit pedantic here going through all the steps because this equation looks like this equation. It just has primes. But now I know that CA prime of 0 is 0 by definition because it's an initial condition, because it's a prime variable. Now let's Laplace transform. Well, except now I know that CA in prime is A sine omega. So let's Laplace transform. What's the Laplace transform of dCA prime dt? Volunteer? What's the Laplace transform of the derivative? Somebody? S times CA prime tilde plus 1 over tau CA prime tilde. And that's equal to 1 over tau times A over tau times the Laplace transform of sine omega t. Can someone look that up for me in the table? What is the Laplace transform of sine omega t? Please make sure you bring that to class and have it handy. That's why I printed it out for you. When you participate, you learn better. If you just copy, you don't learn anything. So what is the Laplace transform of sine omega t?
It's omega divided by s squared plus
Omega divided by s squared plus omega squared. Okay, so now I'm going to factor this out. So this is equal to CA prime tilde times 1 plus s tau over tau. That's the left-hand side. And I have CA prime tilde is equal to tau over 1 plus s tau times A over tau times omega over s squared plus omega squared. And these taus cancel. So notice, if I want to invert this, let's just invert of t. The A comes along for the ride, A omega. But I have a 1 over 1 plus s tau, s squared plus omega squared. Someone look in the table and see if you can find that. Look in the table. Should I call on people? Because people are not doing, I'll call on someone who's not obviously looking at the table. And we'll ask why. Why are you not looking at your table? This is really easy. If you want to learn, you participate. If you want to be a secretary, you copy. You want to be engineers, so you have to participate. What line did you find it in? What line? Line 4? Do you see this in line 4? Do you see it, 1 over s squared plus omega squared in line 4? This is reading. I'm not talking about something complicated. Reading. In the back? What line is it in? You're the only one in the back. All right, where's your table? Okay, did I photocopy it for nothing? I photocopied it so you would have it in class every class, so that you could follow along and actually participate in the class. If you want to learn, the only way to learn is to participate. Yes? What number line is it? $14? Does 14 of this form, s squared plus omega squared, 1 plus s tau? This is reading. This is not calculations, this is reading. Yes, in the Nike shirt, in the Nike sweatshirt. Is that a Nike? Yeah. Do you see this in the table somewhere? Where is your table? Why didn't you bring the piece of paper? I photocopied it because it's easier to deal with the piece of paper than to hunt on the screen. Go ahead. Line 16. Okay, You're to bring this page to class, every class, and when I ask you to look something up, you look it up. I mean, this is not complicated. If you want to learn, you have to be prepared to learn. And you have to bring to class, it's not that heavy, this one page. Okay, so now I invert this, and when I invert it, I just look at the left-hand side. I see omega tau times e to the minus t over tau over 1 plus omega squared tau squared plus sine omega t plus phi divided by the square root of 1 plus omega squared tau squared, where phi is equal to the arctangent of minus omega tau. Okay, now, right now we don't know where that comes from, but let's look at the answer. So if we look at the answer, what we see is the following. First of all, there's one term that decays with t, decays exponentially. So at long times, this term disappears because as t goes to infinity, e to the minus t over tau goes to 0. So this is the transient term. This is the long-term term. And let's notice what it does. This says, if you remember, we have CA in. And now I look at CA out. CA prime of t. 0. And let's notice what's going on. Now I have a sine function output, but it's not sine omega t, it's sine omega t plus phi. So it doesn't start oscillating immediately here, it takes a little longer. And then it starts oscillating. So this difference is indicative of phi, but it's the wrong units. This is time, t. And this thing is telling me something about phi. It's phi, but phi has units of radians, not time, not seconds. So I need to convert it, and I'll convert it in a little while. Yep. Please, you have to take your mask down. I can't hear you.
The table that you gave us, this formula is not.
Yes, it is. It's line 16. Line 16. Look at line. Look at line 16. Huh? I photocopied this out of the textbook. I have the same one you have. I have it right here. I photocopied it. Line 16. The right-hand side of line 16 is omega over s tau plus 1, s squared plus omega squared. You got me? That's the table. I don't know what you have. There are two different versions of the table. Okay, so it's line 14 in your table. So it's line 14. Apparently, there are two different versions. It's line 14 in your table. Gee, I don't know why there are two different versions, but they're from different. So they have the same. They have the same answer, just in a different order. It's different editions of the textbook. I think I photocopied them at a different. Okay, but it's still in the textbook. Okay, so one thing what we can see here is the frequency of the output is the same as the frequency of the input. So omega is the same, but there's a lag, there's a phase lag. And we have it explicitly here. It's the arctangent of minus omega tau. Moreover, let's look at the amplitude. the amplitude here, A, and the amplitude here is B. E is the amplitude, which is A over this thing. E is A divided by the square root of 1 plus omega squared tau squared. So here, by doing the inverse, we're able to explicitly answer the three questions and illustrate what they are in terms of the curve. So we can see that the amplitude B, or the amplitude ratio B over A, which is called the amplitude ratio, is equal to 1 over, in this case, the square root of 1 plus omega squared tau squared. The frequency is the same, and the phase lag is equal to this. So in this case, by doing the inverse, we were able to get all these things. And what we're going to spend the rest of the hour doing is showing that I didn't have to do this inverse to get it. I can do it in general, answer these three questions without doing the inverse. But I wanted to illustrate once what it was. Now I need to do this, this little transformation. I tell you that this delay here, which is the delay from when this started to when this started, or if you like, it's the delay from the first peak to the first peak, or from the first trough to the first trough. Since they're going at the same omega, they progress in the same way. It's all going to be the same. I want to write phi in terms of radians rather than in terms of time. Yeah. Where did I get the B from? It's the amplitude of an oscillation. The sine is amplitude 1. So here the amplitude of the oscillation is its multiplying sine. So over here, the output is also a sine, that is amplitude 1. And I need to know the coefficient that's multiplying it. What's multiplying sine is A over the square root. And that's the amplitude. If I had nothing multiplying it, we would have amplitude 1. By multiplying it by A over the square root, I get the amplitude of the oscillation. Okay, so let's translate this phi, which here it seems to be in time. This says units of time. I want to get it in terms of radians. Well, notice that this distance, phi, the way I convert time to radians is I multiply by radians per unit time. So if I want to get radians, that's equal to radians per unit time times time. Radians per unit time is omega. And the amount of time here, let's call this p prime. The amount of, in units of time. So, and this is p prime. And phi is related to omega p prime. Now, if I notice that this is responding after this. For it to respond after this, I need to have it minus something. The number of radian, the amount of time later would be, if I want something in the past, I have to say t minus t prime. It happened t prime seconds ago. Because I've written p prime as a positive number, or phi as a positive number, with a plus sign in front of it, phi has to be negative. Why does phi have to be negative? Because sine of omega t, I want not omega t in the future, I want omega t in the past. So I have to subtract something from it to say it's from the past. So I need phi to be negative. And phi is minus omega p prime. Now, I don't have to measure p prime all the time. I can notice that in all these oscillations, if I have a time difference of p for one entire period, then 2 pi is equal to omega p. That's just the distance between peaks or troughs. And by doing that, I can divide out and eliminate the p and eliminate omega. So what I get here is phi is equal to minus 2 pi p prime over p. So you could write this however you like, but here I relate it to things on the curve. Phi is 2 pi minus 2 pi p prime over p. Or if you like this better, you can say phi is minus omega p prime. Either one, whichever one you like. But I just wanted to give you graphically a picture of what p prime and p are. Any questions on that? Okay, so what I'd like to do now is go through and show you that you don't have to do the inversion. You can get all this information directly from G. Any questions before I do that? Okay, so show. By the way, by doing this, so for example, what's useful about this? What's useful about knowing the answer? For example, I might ask, I have a certain magnitude oscillation here, and I might want to ask, how big should the tank be so that the oscillation, the magnitude of the oscillation of the output is small, even if this is big? So that the ratio of B over A is 1/10. I might want B over A to be 1/10. So even though I have an oscillation coming in, I want the oscillation coming out to be 1/10 as big as the oscillation coming in. Well, if I know B over A, then I could just set this thing equal to 1/10. If I set it equal to 1/10, omega is known, I just solve for tau. What tau will make it 1/10? And tau, remember, is big V over little v. So it tells me how to adjust the volumetric flow rate or how big to make the tank so that the output over the input magnitudes, the amplitude ratio, is less than 1/10. So hopefully I don't have to write that out, but that's sort of straightforward. But I could ask other questions also. I could ask questions such as, I don't want there to be a big phase lag, or maybe I want my phase lag to be 2 pi, so that way the maxima will correspond. If I do that, then, well, how do I choose tau so that my phase lag is 2 pi, so that the peaks correspond? Well, I take the arctangent of this thing and I set equal to 2 pi, and then I try to find the tau that gives me a 2 pi value. So those are questions I can certainly ask. Or if I want them to be 90 degrees out of phase. When one is a maximum, I want the other one to be a minimum. Well, I set this equal to pi over 2, and I just solve for tau. So those are the types of questions I might ask. We'll see later in the semester why I might want the different values of phi. Okay, so now let's show we can answer, what question number is it? Question 4. Without inverting the Laplace transform. And I'm going to make some assumptions. I'm going to assume, one, the system is stable. If the system's unstable, I'm not worried about the oscillation, it's going to blow up. So I'm going to assume the system is stable. I'm also going to assume that the input is a sine function. I could do it for a cosine, I could do it for a sum of sines and cosines. Anything that oscillates, generally I could break up into a sum of sines and cosines. So if I know one term, if I know how to do one term, I can do any of the other terms. And I can do the sum. So I'm only going to look at the simplest case. Without loss of generality, I can do that. And finally, I'm going to assume that G tilde of S is N tilde over D tilde, both polynomials. Okay, so now let's notice what the answer looks like. once I come up with my solution for y prime tilde. So y prime tilde of s is going to be n tilde of s over d tilde of s times x prime tilde. Where this thing is g. That's just the definition. We said, remember, g is y prime over x prime, so y prime is g x prime. Y prime is g x prime, and g is just n over d. So once I break this up with partial fractions, so I break it up with partial fractions. And then if I did the inverse, which I'm not going to do in detail, but the inverse is going to look like, what's the inverse going to look like? Y prime of t is going to be a bunch of terms that look like a1 e to the alpha 1t plus a2 e to the alpha 2t plus dot dot dot. So those are the terms where the alpha 1, alpha 2 are the zeros of the denominator, assuming they're all different. And then I'm going to have a bunch of other terms that look like b1 e to the alpha e to the beta 1t plus b2 plus b11, b11, b12 t e to the beta 1t plus b13 t squared e to the beta 1t plus dot dot dot. A bunch of terms like that, and those are for the multiple roots. So there, beta 1, beta 2 are the roots of the denominator d tilde that are multiple roots that come in more than once. And then I'll also have terms that look like c1 e to the gamma 1t times, I need a c1 a sine omega 1t plus c1b cosine omega 1t plus similar terms. Yeah, beta 1, beta 1, 2, beta 1, 3, because I have a bunch of terms. Can I finish the sentence, please? Because I have a bunch of terms, when I have a multiple root, if you remember, if I have a root that appears 3 times, then I have 3 terms. So I need 3 terms corresponding to the same root. So if beta 1 is the root, then I need 3 terms that correspond to it. So if it's a triple root, then I have something with t to the 0, t to the first, and t to the second. Question?
No, I was asking for these words on the E, that's why, because I couldn't see it.
I can't understand it.
No, on the beta, on the explode of the E.
Yeah?
Is they're changing also? Because I
No,
couldn't see it.
no, because this is all the same root.
Okay.
It's a multiple root. Because it's a multiple root, it has multiple terms. So each term means another coefficient, but which we wrote out explicitly, but the exponent stays the same. And of course, from each root that's multiple, I'll have another set of terms that look like this. So I'll also have a similar set for beta 2 if there's a second root that is a multiple root. Other questions? Okay, then I have terms that look like this for the ones where the roots are complex. And similarly, I can have other terms where I could have other terms where I have, these are C's, I have D's. E to the gamma delta, delta 1t, C1, 1a, sine omega 1t plus C11e, cosine omega 1t, plus e e to the delta 1t t, c1 2a sine omega 1t plus c1 2b cosine omega 1t, plus more terms like this. This one I didn't do explicitly in class. This is if I have complex roots that are multiple roots. So then I'll also get not just the exponential times sine and cosine, but the exponential times t to a power times sine and cosine. So here's t to the first, then I'll have something times t to the second, etc. And all of these terms so far, all of these terms, all come from g tilde. Because g tilde, we said, is stable. So that tells me that all the alphas are negative, all the betas are negative, all the gammas and deltas are also negative, because that's by assumption it's stable. But now I also have the roots from x prime. And remember, this is a sinusoid Lindbergh. So what I get here from the x prime, this thing is x prime tilde, is I have plus a, b, c, good. I still have d. So plus d1 over something plus d2 over something. These two come from x prime tilde. And let's notice, remember, we can break this up. This was something, if I remember, s squared plus omega squared. So let's recall. Is s minus I omega times s plus I omega. And I factor it. Why is that? Because when I multiply s squared minus I squared omega, I squared is minus 1, so minus 1 is omega squared. Plus si omega minus si omega. So that's what I get there. So remember, this is in the denominator. It's in the denominator. So each factor gets its own term. So I have a d1 over s minus I omega. Like we said, over s plus I omega. Plus d2 over s minus I. Where these terms come from x prime tilde. Now, again, everything here is stable. So what I'm really looking at is what's going on here. Stable means exponentially disappears at infinite time. So like this term, exponentially disappears at infinite time, transients. So it tells me this only gives me transients. If I'm looking at the long time behavior, I want to look at what persists. And what persists comes from the input. It comes from here. So it comes from these terms. So I need to determine what d1 and d2 are and look at what this is going to give me in the inverse. And let's recall that 1 over s minus alpha gives me e to the alpha t. Okay, so let's look at d1. Let's see what d1 is. Well, if you remember, the way I get, when I was doing partial fractions, when I had m tilde of s was equal to m1 tilde of s over s minus alpha plus stuff. I'm sorry, yeah. Then, I'm sorry, it was C1. I found that C1, let's call it D1 here. D1 was equal to M1 tilde of S, M tilde of S, divided by, with S minus alpha evaluated at S is equal to alpha. In other words, obviously I can't put S minus alpha in, S equal to alpha here, but I take that factor out of n tilde. So now n tilde does not, over this, does not blow up at s is equal to alpha, because this is a simple root. So what I do is I take everything but s minus alpha. There are no more s minus alphas in there, so that thing makes sense. So let's do partial fractions. Here I have d1. Maybe I should use d. I should use c. I don't know. Doesn't matter. Okay, so let's go back to our problem. So I have d1 from here is equal to, well, it's everything else besides the s minus alpha. And this, remember, s plus I omega is equal to s minus I omega. So the alpha is minus I omega. So it's equal to g tilde, everything in g. This thing was g tilde. Evaluated at minus I omega. Everything in g. And the other factor that came from x prime, because I only take out the s minus alpha. So it's divided by s minus I omega, evaluated at s is equal to, why don't we say, s evaluated at s is equal to minus I omega. Is that clear? I'm doing exactly this rule. I take all the other factors in my answer, all the other factors in here except s minus alpha, and I evaluate them at s is equal to alpha. And by definition, since it's a simple root of the denominator, and I've canceled all common roots, that thing is finite. Similarly, D2 is, this is s minus plus I omega. So the root here is plus I omega. So I take everything else, g tilde of s over s plus I omega, and evaluate it at s is equal to I omega. And now I can do, now I can write this together. So I have d1 over s plus I omega plus d2 over s minus I omega is equal to, it's equal to g tilde of minus I omega over, now minus I omega is minus 2 I omega times 1 over s plus I omega plus d2 g tilde of plus I omega over I omega plus I omega is 2 I omega, 1 over s minus I omega. And now when I invert this, this thing becomes e to the minus I omega t, and this thing becomes e to the plus I omega t. Okay, well, let's also notice that I had an omega. I had an a omega times this whole thing. So let's just not lose the a omega. I had an a omega times everything. So this is divided by a omega. So now when or why don't I multiply everything on the right by a omega? This whole thing, I don't know how to, this a omega, for instance, all this thing is multiplied by a omega. So let's just put the a omega in here, because that's y prime of t is going to come from here. So let's not forget I have an a omega. And the omega cancels. So, are we all together? All right, so let's now look at g tilde of I omega and g tilde of minus I omega. G tilde of I omega, we said, notice that minus I omega is the complex conjugate of plus I omega. So I omega bar is minus I omega. Moreover, we showed in an earlier class that if I have a polynomial of z bar, that's equal to the polynomial bar of z. And similarly for the ratio of polynomials. So as a result, g tilde of minus I omega is equal to g tilde bar of plus I omega. In other words, this is the complex conjugate of this. And that's based on what we showed in an earlier class, that the complex conjugate of the product is the product of complex conjugates, and the complex conjugate of a sum is the sum of the complex conjugates. And I ask you to show for homework that the complex conjugate of a ratio is the ratio of the complex conjugates. And that's how you get it. So, as a result, g tilde of I omega is some complex number. So g tilde, let's go into the complex plane. I've got the reals and I've got the imaginaries. And I have some complex number, which I'm going to call g tilde of I omega. Now, that has a magnitude. It's got the magnitude. And it has an angle, phi. And the complex conjugate, remember, the complex conjugate says I flip the imaginary part to its negative, and I leave the real part the same. So that means I take the mirror image about the real axis, because I'm flipping I to minus I, but I'm leaving the real part the same. So this now is minus phi. And this is the complex conjugate, g tilde of I omega bar. It's got the same magnitude. It's got the same magnitude, but the angle has been flipped, so I have the bar here. So that tells me if I write g tilde of I omega as its magnitude times e to the I phi, then g tilde of minus I omega, which is just the complex conjugate, is g tilde of I omega magnitude times e to the minus I phi, because I just flipped the angle. And let's notice what phi is. Phi, notice I have a right triangle here. This is the real part, and this is the imaginary part. So phi is the arctangent of the imaginary part over the real part. So where phi is the arctangent of the imaginary part of g tilde of I omega, divided by the real part of g tilde of I omega. Just a little bit of geometry. So let's see where we're going. We have that y prime of t at long times is equal to. So I have the a. That comes on the outside. And now I've got g tilde of I omega. G tilde of I omega, we said I'm going to write it as the magnitude of g tilde of I omega times e to the I phi. That's this. Divide, and it's going to be divided by 2i. So that's g tilde of I omega over 2i times e to the I omega t. When I multiply two exponents together, the things in the exponent add. Is that clear how I got that? G tilde of I omega, I plugged in its magnitude times e to the I phi. e to the I phi times e to the I omega t is e to the I phi plus omega t. And the 1 over 2i comes along for the ride. We just did this term. Now let's do this term. So now, first I have a minus sign here. Minus. I've got a 1 over 2i. That comes along for the ride. I've got a g tilde of minus I omega. The g tilde of minus I omega is the magnitude of g tilde of I omega times e to the minus I phi. And that's multiplied by e to the minus I omega t. Is that clear? You can ask questions, you're allowed to. Again, these are mathematical manipulations. I'm doing them probably a little faster than some of you can catch it at the moment. But at least try to get the technical steps. And if there's any problem, you could always ask next time. Remember, I come here to answer questions 45 minutes before class. Okay, so now let's notice I can factor out the g tilde of I omega. Magnitude. Now what am I left with? I'm left with e to the I phi e to something, e to the I something minus e to the minus I something over 2i. What is e to the I something minus e to the minus I something over 2i equal to? Which we've had already. What is that equal to? Someone has to pull their mask down. Tell me. Don't be afraid. If you get it wrong, it's not the end of the world. What is e to the I something minus e to the minus I something over 2i equal to? It's sine. This is, so what I have is that y prime of t at long times is equal to a magnitude g tilde of I omega times sine omega t plus phi. And that is exactly the pot of gold at the end of the rainbow. Why is that? Because I can answer question 4 exactly from here. Question 4. The first thing I know is if the, remember, x prime of t was equal to a sine omega t. So the first thing I know is that the output frequency, omega, is the same as the input frequency. So, answers. Omega, answers. So 4. A, omega out equals omega in. That's only true for linear processes. If I had nonlinear models, that wouldn't be true. So it's only true for linear and linearized models. Second part, I asked about the omega. The second thing I asked about was the amplitude ratio. Well, the amplitude of the input was A. The amplitude of the output is what's multiplying the sine function. What's multiplying the sine function is A times g tilde of I omega. So B is B over A is equal to just g tilde of I omega magnitude. That is, I don't have to invert the Laplace transform. As long as I know what g is, or g tilde, as long as I know what g tilde is, I evaluate it at I omega, and I take the magnitude. Finally, phi, the phase lag, which we did in these pictures here somewhere. Where did phi go? Over here. This phase lag, that phi is equal to the arctangent of the imaginary part of g tilde of I omega over the real part of g tilde of I omega. So what does that tell me? That tells me I can answer question 4, all of it, let's do some examples. Notice here we did it in gory detail. Let's notice what was G here. Let's see what G was. Well, G was pretty easy. G was 1 over 1 plus S tau. Because it was a CSTR, G tilde. So G tilde was 1 over 1 plus S tau. I need space on the black line. Space, the final frontier. Can you arrange? Now, I'm going to need to know the real and the imaginary part, because I need that for phi. So, the way I get a real and imaginary part is I need an I in the numerator. I's in the denominator don't help me. That just confuses me. So to turn this into something where I is in the numerator, not in the denominator, I multiply top and bottom by the complex conjugate, 1 minus I omega s. When I multiply that, then the denominator becomes 1, this and this cancel, and what I have left in the denominator is, I'm sorry, not s, it's tau. S was I omega. And then here I have minus times a plus is a minus. I squared is another minus. Minus squared is plus. So 1 plus omega squared tau squared. And here I have 1 minus I omega t, omega tau. So is that clear what I did? And now let's look at what B is. B over A. B over A, we say, is just the magnitude of G tilde of I omega. It's the magnitude. Well, the magnitude is this thing, the magnitude. So this is a right triangle. By Pythagoras' theorem, the magnitude is the square root of the real part squared plus the imaginary part squared. Just by Pythagoras. So B over A is the square root of 1 over this thing squared plus this squared over this squared. So the denominator just stays 1 plus omega squared tau squared. And the numerator is the square root of 1 squared plus the imaginary part, omega minus omega tau squared. Well, the minus cancels when I square it. And I have 1 plus omega tau squared. This is the square root of 1 plus omega squared tau squared over 1 plus omega squared tau squared. And I just get 1 over the square root of 1 plus omega squared tau squared, which is exactly what I found here. B over A, we said, is 1 over the square root of 1 plus omega squared tau squared. Moreover, phi is the arctangent of the imaginary part over the real part of G tilde of I omega. Well, the imaginary part is this, and the real part is this. They both have the same denominator, so they cancel. Well, let's write it out. Minus the arctangent of minus omega tau divided by 1 plus omega squared tau squared. Divided by, that's the imaginary part, the real part is 1 over 1 plus omega squared tau squared. The denominators cancel, and this is just the arctangent of minus omega tau, which is exactly what we found here. And now we get it in general. This and this agree with this and this, as they have to, because we proved it. Questions? Let's do another example. Let's say I have 2 CSTRs in series. Two CSTRs in series. So in this case, and say volume 1 is equal to V2, then I know that G tilde of S is equal to 1 over 1 plus K tau 1. Well, 1 over 1 plus, they're the same, so it's 1 over 1 plus K tau squared, divided by 1 plus S T squared. Where here I can have a reaction. let's say I have a reaction. So this is with reaction, with first order reaction. And this thing I'm just going to call Kp. Kp2. So let's, so this is just Kp2 over 1 plus St squared. Okay, so what's G tilde of I omega? That's Kp2 divided by 1 plus I omega T squared. Well, that's just the square of this. So I don't have to do the algebra again. I can just, okay, I can do the algebra again. Okay, so I'm going to multiply by 1 minus I omega T squared. 1 minus I omega T squared. So what do I get here? This is equal to Kp2. Now, the denominator is just the square of this denominator. So it's 1 plus omega squared T squared squared. Because it's exactly this thing, just squared. And now I have to square the numerator. So when I square the numerator, I've got a 1 times 1. I've got minus 1 squared is plus 1, minus omega squared T squared. Plus I times minus omega, this thing times this twice. So minus 2 I omega T. So notice I did that to get the i's out of the denominator and get them in the numerator. So what can I say about that? What I can say is, the first thing is that B over A, which is the magnitude of G tilde of I omega, is the magnitude is the square root of the real part squared plus the imaginary part squared. Well, the square root of this thing squared is just itself. And here I have the square root of 1 minus omega squared T squared squared plus minus 2 omega T squared square root. And you could work that out. That's exactly what that is. Well, I can work it out too. So let's work it out. So I've got 1 plus omega squared T squared. And here I have the square root. So here I have 1 plus omega 4 T4 minus 2 omega squared T squared plus 4 omega squared T squared minus 2 plus 2, minus 2 plus 4 is plus 2, and 1 with the plus, this is just 1 plus omega squared T squared squared. This just becomes 1 plus omega squared T squared divided by 1 plus omega squared T squared squared. Because 1 plus 2 omega squared T squared plus omega fourth T to the fourth is just the square of 1 plus omega squared T squared. And this just becomes 1 over 1 plus omega squared T squared. Because this cancels out. So this is B over A. Questions? And let's do 5. 5 is the arctangent of the imaginary part over the real part. Is the arctangent. Well, the imaginary part, they both have the same denominator, so they're going to cancel. The imaginary part is minus 2 omega t divided by 1 minus omega squared t. The imaginary part is this over this, and the real part is this over this. So the bottoms cancel, and I just get that. Questions? one more example, and then we're done for today. Let's look at a plug flow reactor. With no reaction. So if I have no reaction, then whatever comes out is just whatever went in tau seconds later. This is no reaction. So y prime of t is just x prime of t minus tau. Whatever came in tau seconds ago goes out. This is a pretty boring reactor. Nothing special. Well, we know that y prime tilde of t. What is the Laplace transform of a delay? What did we say the Laplace transform of delay was? You all have your table, yes? Go ahead. What was the, I thought you raised your hand. What's the Laplace, you have your table. What's the Laplace transform of a delay? If you don't participate, you don't learn. Besides, you also have to look at your notes from previous classes. We did this on the blackboard. If you try to learn it all the night before the exam, you get the results we got on the first exam. You have to, before class, sometime in between now and Tuesday, go through your notes from this class, between now and Wednesday. What is the, yeah?
Delay in this case is t minus tau, so that it would be e to the minus tau s times.
Good. E to the minus s tau times x prime t, tilde of s. So that tells me g tilde of s, which is y prime tilde of s over x prime tilde of s, is equal to just e to the minus s tau. So let's notice what b over a is. So now if I have a sign coming in, what comes out? Well, that's the magnitude of g tilde of e to the, of I omega, which is the magnitude of e to the minus I omega tau. Well, remember, e to the I times something is a cosine plus I times a sine. So this is equal to the magnitude of the cosine of minus omega t, which is just the cosine plus omega t, plus I minus I times the sine of omega t. The magnitude is the cosine squared plus the sine squared. What's the cosine squared plus the sine squared? 1. So this is just equal to 1. So we know that the magnitude of e to the I times something is always 1. So that says if I have a sign coming in, I have the same sign coming out that is the same magnitude. The amplitude is the same. Moreover, the phase lag is the arctangent of the imaginary part. The imaginary part is minus sine omega t, tau, over plus cosine omega tau. So it's the arctangent of minus the tangent of omega tau. Well, minus the tangent is the tangent of minus, because the sine function is an odd function and the cosine function is an even function. So this becomes the arctangent of the tangent of minus omega tau, which is just minus omega tau. Which makes sense. The phase lag is just translating tau, the time it takes to get through here, into radians, which means I multiply by omega. So I just get, and it's negative because phi is generally negative, because the output happens later than the input, not earlier, so it's negative. Are there any questions? Please.
I'm missing how you're saying the cosine squared plus sine squared are negative one, but it's not. Why are they squared?
It's the square root of this. How do I get a magnitude? A magnitude is I take the square root of x squared plus y squared. So x squared plus y squared is 1. So the square root of 1 is 1. Remember, it's by Pythagoras' theorem. I want the size of this. So I take x squared plus y squared and the square root. X is cosine, y is minus sine. So I get cosine squared plus minus the square of minus sine squared, which is the same as sine squared. Cosine squared plus sine squared is 1. The square root of 1 is 1. Of course, there's also minus 1. The magnitude is to be greater than or equal to 0, so I choose that. The positive. Are there other questions? Okay, there's a little bit of math to digest here. So please make sure that between classes, you look back at your old notes. And then I'm here 45 minutes before class. Anything you didn't understand or you're not sure about, just ask. But that way, once I start the new class, you'll be prepared. And I will give you some homeworks today. I should have given them last time, but I'll give you homeworks today. Other questions?